Smaller aircraft use ailerons for control in roll, but the majority of modern high-speed jet transport aircraft use a combination of ailerons and spoilers. You may consider this a strange-looking aeroplane, but the two halves of the wing and the cockpit control have been displayed this way to give as large a view as possible. Also, the aileron displacement shown in the following illustrations is emphasized for clarity and is much bigger than that required in practice. If the control wheel is moved to the left aileron moves up. This decreases the camber of the wing in the vicinity of the aileron and reduces lift. At the same time, the right aileron moves down. This increases the camber of the wing in the vicinity of the aileron and increases lift. The difference in lift on the two halves of the wing generates a rolling moment to the left, and the aircraft will start to roll to the left. If you were to hold the ailerons displaced from neutral like this, the left rolling moment would still exist and the aircraft would continue to roll to the left about the longitudinal axis. In normal flight, not something you would want to happen. Clearly then, ailerons are not a displacement control like the elevator. Ailerons are a rate control. If ailerons are displaced from neutral only slightly, the aircraft will roll slowly. The greater the aileron displacement, the greater the rate of roll. Usually, you roll the aircraft to a given bank angle to change heading, in other words, to turn. To hold a given bank angle, you must reduce the rolling moment to zero by returning the ailerons to neutral. Please bear in mind that we are presenting only the principles of flight. When you start flight training, your instructor will show you what is actually required to hold a constant bank angle, but don't worry, it's not fundamentally different. Just before you reach your desired heading, to allow for the time taken to roll the aircraft back to wings level, you turn the control wheel to the right. The left aileron moves down. This increases the camber of the wing in the vicinity of the aileron and increases lift. At the same time, the right aileron moves up. This decreases the camber of the wing in the vicinity of the aileron and decreases lift. The difference in lift on the two halves of the wing generates a rolling moment to the right, and aircraft will start to roll to the right, in this case back towards wings level. Just before you get to wings level, you neutralize the ailerons, which reduces the rolling moment to zero, and the aircraft will stop rolling. We will now look at the byproducts of rolling the aircraft about the longitudinal axis. The first consideration is our old favourite, aerodynamic damping. We will assume a constant IAS, but you should remember that aerodynamic damping is a function of TAS, not IAS. Please note the true airspeed vector. Only the downgoing wing is illustrated. The opposite will take place on the upgoing wing, but will have the same effect. The aileron has been moved up to generate a downforce. The aircraft will begin to roll. This wing is now moving downwards in addition to moving forwards. The black vector represents the downward speed of the wingtip. The blue vector represents the effective airflow and is the resultant of the TAS and the rate of roll. The angle between the TAS vector and the effective airflow vector is the change in effective angle of attack. This increase in effective angle of attack on the downgoing wing generates an up-force called aerodynamic damping. Aerodynamic damping reduces the rate of roll. When the aircraft stops rolling, there is no longer any aerodynamic damping. At a constant IAS, a higher altitude will require a higher TAS. The same aileron deflection will produce the same aileron force because the IAS is constant. But because the TAS is higher, the increase in effective angle of attack is smaller. This results in reduced aerodynamic damping and consequently a higher rate of roll. To achieve the same rate of roll with an aircraft of greater wingspan, the ailerons must be deflected through a greater angle. Because the wingtip is further from the CG, the wingtip has to move downwards through the air faster, increasing aerodynamic damping. The second byproduct of rolling the aircraft about the longitudinal axis is adverse aileron yaw. The objective when rolling the aeroplane is usually to turn to a different heading, as previously described and here animated. If both ailerons move through the same angle from neutral, the downgoing aileron will generate more drag than the upgoing aileron. Parasite drag is the same on both, but the downgoing aileron would generate an increase in induced drag, and the upgoing aileron would generate a decrease in induced drag. Only the downgoing aileron is illustrated. The adverse aileron yaw illustrated here is greatly exaggerated for clarity. The result of adverse aileron yaw is a yawing moment in the opposite direction to that required. If you roll the aircraft, in this case to the left, a yawing moment to the right is generated. This is both aerodynamically inefficient and physically uncomfortable for all on board. It must be pointed out, it's only during the roll, while the ailerons are displaced from neutral, that adverse aileron yaw occurs. Aircraft designers can reduce adverse aileron yaw in several ways. The first method we will look at is differential ailerons. The downgoing aileron moves through a smaller angle than the upgoing aileron. This reduces the difference in drag. Nearly all aircraft have differential ailerons. The second method of adverse aileron yaw reduction we will look at is the freeze aileron. The leading edge of the upgoing aileron projects below the wing, increasing the parasite drag. The downgoing aileron does not project into the airflow. It can be seen that freeze ailerons also reduce the difference in drag. Freeze ailerons are usually used together with differential ailerons on small and medium-sized aircraft. The third method of adverse aileron yaw reduction we will look at is aileron rudder coupling. Aileron rudder coupling is usually used on large modern aircraft. There is an interconnection between the ailerons and the rudder, such that when a roll input is made, the rudder is automatically deflected to cancel the adverse aileron yawing moment. Note, the difference in drag from the ailerons still exists. The fourth and final method of adverse aileron yaw reduction we will look at is roll spoilers. Most modern high-speed jet transport aircraft use roll spoilers to assist the ailerons with roll control. The operation of roll spoilers will be fully explained later. As you can see, the spoiler surface comes up on the side with the upgoing aileron, matching the drag on the two sides and thus reducing adverse aileron yaw to a negligible amount. You have seen that ailerons are mounted as far outboard as possible to give the longest arm from the CG. This is done to minimize aileron size and the angular displacement required for a given rolling moment. Unfortunately, this wingtip location also maximizes the ability of the ailerons to twist the wing. The downgoing aileron increases the camber of that part of the wing with the objective of generating an up force on the wingtip to roll the aircraft. But the wing twist will decrease the wing incidence and reduce the roll force. If we consider a higher IAS, the wing twist will be greater for the same aileron displacement, further reducing the rolling moment. Eventually, an IAS will be reached when the effect of the aileron is cancelled by the effect of the wing twist and the aircraft will not roll when commanded by the pilot. Higher IAS will give a larger rolling moment from the wing twist than from the ailerons, and the aircraft will roll in the opposite direction to that commanded by the pilot. This phenomenon is called high-speed aileron reversal and would limit the maximum operating speed of the aircraft. Making the wing stiffer to increase the IAS at which high-speed aileron reversal occurs is not an option because it would increase the structural weight of the aircraft. Instead, another pair of ailerons is fitted further inboard on a stiffer part of the wing. These are called inboard ailerons. At low indicated airspeeds, you can see that both the inboard and outboard ailerons operate through their full angle of displacement when commanded from the flight deck. We can see that the aeroplane is flying slowly because the trailing edge flaps are down. After takeoff, the aircraft is accelerated, and when the IAS reaches the speed at which the aircraft can fly safely with the flaps up, the flaps are retracted. As the flaps retract, a mechanism reduces the input to the outboard ailerons. So, as the trailing edge flaps retract, the outboard ailerons will move through a progressively smaller angle than the inboard ailerons. With the flaps fully retracted, the outboard ailerons no longer move, only the inboard ailerons. To complete your understanding, please note the following. The reduction in outboard aileron movement with decreasing trailing edge flap angle is referred to as locking out the outboard ailerons, as in, flap retraction locks out the outboard ailerons. Outboard ailerons can also be called low-speed ailerons. Inboard ailerons can also be called high-speed ailerons or all-speed ailerons. The outboard low-speed ailerons only work when the trailing edge flaps are down. When the trailing edge flaps are retracted, the outboard low-speed ailerons are locked out. The inboard high-speed, all-speed ailerons always work. Please review this scene several times to ensure you remember the complexities. You have previously been shown that flaps are fitted to the trailing edge of the wing, and you have now been shown that ailerons also occupy part of the wing trailing edge. The resulting reduction in flap area reduces the efficiency of the flaps. On large, modern high-speed jet transport aircraft, this reduction in flap area is a significant disadvantage, so design changes have been made to make the ailerons also work as flaps. Hence the name flaperons. When the trailing edge flaps move down, the flaperons also go down. Now the whole wing area has its camber increased, thus maximising the effect of the flaps to increase CL max. But what about lateral control? Think of the flaperon position with the flaps down as a new neutral datum. When a roll input is made, the flaperons move up and down from this new neutral datum and still provide a change in lift on both halves of the wing for roll control. Spoilers are usually fitted to large, modern, high-speed jet transport aircraft to help the ailerons with roll control. Spoilers are movable panels on the top of the wing. They are hinged at their forward edge and activated hydraulically. When raised into the airflow, spoilers spoil or disturb the airflow, thus decreasing lift and increasing drag. Roll spoilers are activated by the control wheel and move up on the side with an upgoing aileron, proportional to aileron displacement. You can see that the roll spoilers on the side with the downgoing aileron remain flush. Even with the flaps up, the roll spoilers continue to assist the ailerons with roll control. Roll spoilers have several advantages over ailerons. Roll spoilers eliminate adverse aileron yaw. Roll spoilers do not twist the wing. Roll spoilers do not develop flutter. Roll spoilers do not take up space on the trailing edge, leaving it usable for flaps. Because spoilers work by reducing lift, their use will always result in a net loss of lift on the wing. This is not normally a significant disadvantage. When selected by the pilot, speed brakes increase drag. The use of speed brakes increases deceleration and/or gives an increase in the rate of descent without increasing the IAS. There are two common methods of mounting speed brakes: wing-mounted or rear fuselage mounted. Ideally, speed brakes should give an increase in drag without affecting lift or causing a change in pitching moment. Fuselage-mounted air brakes are best suited to do this, but are only occasionally used on civilian transport aircraft. Modern high-speed jet transport aircraft usually use the spoiler surfaces on the wing as speed brakes. There is a speed brake lever on the flight deck that, when selected to up by the pilot, extends the speed brakes symmetrically, thus increasing the drag. There are no speed restrictions for the operation of speed brakes. However, the design of the hydraulic operating system does give a blowback facility. That is, for the same selection from the flight deck, increasing IAS restricts the speed brake angle of deflection into the airflow. This prevents excessive buffeting at higher IAS. While being used as speed brakes, the spoiler surfaces will continue to assist the ailerons with roll control. To illustrate this, we will pull partial speed brakes. Now, when a roll input is made, the spoiler surfaces will move up or down about the datum of the speed brake selection. In flight, the maximum angle to which the speed brakes can deploy is restricted to prevent excessive loss of lift and excessive buffeting. But as soon as the aircraft touches down, there is a need to remove as much lift from the wing as possible so that the wheel brakes will have maximum effectiveness. In addition, there is a need to increase drag as much as possible. After touchdown, the air-ground logic system senses the aircraft is on the ground and removes the restriction on speed brake angle. When full speed brakes are demanded from the flight deck with the aircraft on the ground, the speed brakes deploy to a much larger angle than in flight. This is called lift dump.